So, welcome to this lecture number 18 in our course on fundamentals of transport processes. We were discussing transport in cylindrical coordinate system. As I explained in some detail in the last lecture, we use curvilinear coordinate systems when the symmetries of the configuration we are analyzing have a cylindrical symmetry. So, when we do that, the surfaces of constant coordinate now become cylinders, constant r. Okay. And the advantage is that now we are applying boundary conditions on surfaces of constant coordinate. Okay. And so, you have chosen the coordinate system in such a way that the surface of the cylinder has a constant radius r. The disadvantage of that is that the differential equation has a slightly more complicated form, because the surface area is changing as the coordinate changes. So, as I change the radius of the cylinder, the surface area changes. This is in contrast to the Cartesian coordinate system, where at every plane within my cubic volume, the surface area was exactly the same. So, last class we looked at the differential equation that results from this. So, these differential equations have a slightly more complicated form. The concentration, the momentum and the temperature equations. The form of the differential operator is more complicated simply because the surface area is changing as the distance changes. Okay. And because of that, if you solve for a steady flow between two cylindrical surfaces, we solved for the steady flow between two cylindrical surfaces in the last lecture, where you have two surfaces, the two walls of a tube. There is an inner surface for this wall and the outer surface. And for these two surfaces, you fix two temperatures. The temperature in between does not vary linearly with position, rather it has a logarithmic variation with position. Okay. So, this was the equation, the solution that we got for the temperature profile in between the two. Okay. And we had seen how we got the log law for the heat flux. Okay. The heat flux is equal to the temperature times the difference in temperatures times the heat conductivity divided by the thickness times an area which is based upon the logarithmic mean radius, okay, r naught minus r I by log of r 0 by r I. Okay. And then we solve the problem of separation of variables in a cylindrical coordinate system. Okay. And I explained to you that this is different from Cartesian coordinates. If I have a Cartesian coordinate system, I have a surface where the temperature is instantaneously increased. And if I consider diffusion from this surface into an infinite medium, there are no length or time scales in the problem, and therefore, I can define transfer in terms of a similarity variable. In the case of a cylindrical coordinate system, even if I have a cylinder in an infinite medium, right, and I consider a temperature difference between the surface of the cylinder and the temperature far away, the temperature in an infinite medium cannot be solved using similarity solution, because the cylinder radius is still a parameter in the problem. So, I can still define a non-dimensional radius as the ratio between the distance and the radius of the cylinder. And therefore, for transfer from a cylinder of finite radius, you cannot use the similarity solution for obtaining a solution. Okay. However, one can consider a cylinder of infinitesimal thickness, a wire whose radius is very, very small. And for this wire, since the radius of the wire goes to 0, one can still use a similarity solution for this equation. However, as the radius goes to 0, if the heat flux or the temperature is fixed at the surface, okay, or if I fix the temperature gradient at the surface, the heat flux is equal to the thermal conductivity times the temperature gradient. If the temperature is finite, the heat flux is finite, the surface area of a wire of infinitesimal thickness goes to 0 as r goes to 0. Therefore, I cannot specify a temperature boundary condition at the surface, because what it would mean is that if the temperature is finite, the total heat coming out goes to 0, because this wire has infinitesimal thickness. Okay. What I need to specify is actually the total heat coming out per unit time. okay, capital Q, which is equal to QR times 2 pi r L, okay, in the limit as r goes to 0. So, as I approach very close to the surface of the wire, the radius decreases, the heat coming out will be per unit time will be finite only if QR is proportional to 1 over r in this limit. Okay. So, this kind of a boundary condition can be satisfied only if my solution of the equation is such that QR goes as 1 over r in the limit as r goes to 0. So, we do not really have a temperature scale at the surface of the wire itself. All we know is that how much heat is coming out per unit time from the surface of the wire. Okay. So, that is all we know at the wire itself. Far away the temperature is a constant, and at time t is equal to 0 the temperature is a constant everywhere. So, this was the differential equation for the temperature field, okay, and we had scaled it and specified the boundary and initial conditions. Okay. I pointed out that there is this additional term here, okay, which is not present in a Cartesian coordinate system, and that comes about because the radius changes and the surface area changes as you go out in a cylindrical coordinate system. And we had defined the similarity variable as r over square root of alpha t. And express the mass the heat conservation equation in terms of this similarity variable. Okay. And we got an equation of the kind d square t by d psi square plus 1 over psi plus psi by 2 dt by d psi is equal to 0. Recall that when we solved the problem in Cartesian coordinate system, the equation was of the form d square t by d psi square plus psi by 2 dt by d psi is equal to 0. That was the equation in a Cartesian coordinate system. In a cylindrical coordinate system, I have this additional term here 1 over psi times d psi by dt, and that is because once again the surface area is changing as the radius changes. And we had two boundary conditions. One is that t is 0 as r goes to infinity or psi goes to infinity, and this 2 pi r L times q r is equal to the heat coming out per unit time from the wire. This in the limit as r goes to 0 at the surface of the wire itself. What is being specified is the total heat coming out per unit length of the wire, not the temperature or the heat flux, because the heat flux cannot be specified because the surface area is going to 0. So, the heat flux is finite, the heat coming out will go to 0, and we solved this quite easily. Okay. This term was not present in a Cartesian coordinate system once again, and therefore, we were able to specify the temperature. But when this term is present, T star actually goes to infinity as you approach the surface. Okay. Despite T star going to infinity, we were still able to find the constant C in the equation. Okay. Okay. And the reason we found the constant C was because once we put the temperature into the equation for the heat flux, okay, once we put the temperature for the equation into the heat flux, we got a temperature field that is going as 1 over r in the limit as r goes to 0. Yes, I am sorry, we were getting a heat flux that was going as 1 over r in the limit as r goes to 0. And because the heat flux goes as 1 over r, surface area is proportional to r, therefore, the total heat coming out is finite in the limit as r goes to 0. Okay. And we managed to get a solution for the total temperature field as well as the total heat coming out. At the surface of the wire itself, the heat is finite. Okay. The heat coming out is finite even though the flux goes to infinity and the temperature also goes to infinity. So, this as I said is the temperature field for a line source of heat. Okay. It is a line source in 3 dimensions. If I just consider the plane perpendicular to the wire itself, what it looks like is a point source of heat from which heat is coming out symmetrically in all directions. Okay. So, this is a point source in 2 dimensions or a line source in or a line source in 3 dimensions. We will see the point source in 3 dimensions when we do a spherical coordinate system a little later. Now, let us look at heat conduction from a finite cylinder. Okay. So, the problem is as follows. I have a cylinder. You can consider this to be of infinite extent in the vertical direction, okay. And the temperature within the cylinder is initially at some value T1. Okay. This is immersed into a bath, okay, where T is equal to T naught. Okay. So, the temperature T is equal to T naught everywhere in the bath. The cylinder temperature is T1. It is immersed in this bath, and as time progresses, the temperature of the cylinder decreases with time. Okay. In the final state, of course, the temperature will be T naught everywhere. Okay. So, in the final state, the temperature is just going to be T naught everywhere. However, initially at time T is equal to 0, the temperature everywhere within the cylinder is going to be equal to T1. Okay. Okay. And only at the outer surface, as soon as it is immersed, the temperature is going to come down to T naught. Okay. Think of immersing, let us say, a cylindrical cup at a high temperature into a vessel with cold water at low temperature. The vessel is large enough that the heat conducted from the cylinder does not change the temperature of the vessel appreciably. Okay. So, that is the kind of problem. Of course, if you solve the problem for a cup, the temperature is going to be a function of height as well. Okay. It is going to be a function of the z coordinate as well, not just the distance r from the center, from the central axis. Okay. So, this is a simplification of that problem, okay, where I have a cylinder with at a temperature T1. At time T is equal to 0, I immerse it in a bath. Okay. So, what are the initial and boundary conditions for this problem? We have already seen what is the heat conduction equation for this problem. What about the initial and boundary conditions? Okay. As the equation is second order in space and first order in time, I require 2 boundary conditions and 1 initial condition. Okay. So, the boundary conditions T is equal to T naught at r is equal to capital R, if capital R is the radius of the cylinder. Okay. If capital R is the radius of the cylinder, then I require that since the cylinder is immersed in a bath at temperature T naught, the temperature at the surface of the cylinder also has to be at the same temperature T naught at r is equal to capital R. Initial condition, I can think of one quite easily. T is equal to T1 for all r less than r at T is equal to 0. What this says is that the moment I have immersed the cylinder, the temperature everywhere within the cylinder is still equal to T1, which was the initial temperature. Okay. Only the surface has come into contact with this bath, whose temperature is at T naught. What about the other boundary condition? I have a second order differential equation in the radial coordinate. Okay. So, I should have another boundary in the radial coordinate. Okay. This is going to be a common feature when we deal with curvilinear coordinate systems. Okay. Because the other boundary should be at r is equal to 0 at the central axis itself. Okay. So, if I have a cylinder with a central axis, okay, I have one boundary condition on the surface of the cylinder, r is equal to capital R, but how about the boundary condition at the central axis of the cylinder? This is not really a boundary. Okay. There is no boundary between the domain and some external region at r is equal to 0. It is entirely within the fluid itself. Okay. The axis is entirely within the fluid itself. At this, so it is at this boundary, it is not really a boundary, but at this boundary in the r coordinate we enforce what are called symmetry conditions. Okay. Let me explain that a little bit. Okay. Now, there is no source or sink of heat along the central boundary, okay, unlike in the previous problem where we had a wire and that wire was emitting heat. Okay. In this particular case, it is just a fluid with an axis going through the center and there is nothing there. Okay. That requires that at r is equal to 0, okay, the derivative of the temperature has to be equal to 0. Okay. Why is that? Okay. This is a symmetry condition. Okay. Okay. Let us assume for the sake of argument that the derivative is not 0 at the center. Okay. So, this is my cylinder, this is my central axis. Okay. So, this is my r coordinate and I will plot the temperature, okay, the temperature as a function of the distance, the radius. Okay. And let us assume for the moment that the derivative of the temperature with respect to radius is not 0 at the center. Okay. So, let us assume for the moment that we have a non-zero derivative at the center. Okay. The derivative of the wall could be 0 or non-zero depending upon the boundary condition there, but we will assume for the moment that the derivative at the center is not equal to 0. So, the slope is not 0. Okay. However, note that there is no change in the temperature field as you go all the way around the axis. We have assumed that the system is axisymmetric. So, there is no change in the temperature field as you go around the axis. Okay. So, if I go all the way around the axis and come to the other side, the temperature field on this side has to look something like this, exactly a reflection of the temperature field on the right side, because the temperature field is independent of location on the axis. So, if I go all the way around, the temperature field on the left side has to be a reflection of the temperature field on the right side. Okay. Note that therefore, the temperature field on this side has to be this. So, just symmetry requires that if the derivative of the temperature is non-zero, that means that the derivative of the temperature is different at different as you approach the center from different locations. Okay. If you approach it from the right, the temperature decreases as I go as r increases. If I approach it from the left, the temperature decreases towards the left. So, the derivative itself is not uniquely specified at the center itself. Okay. The only way that the derivative will be uniquely specified at the center itself is if the derivative is 0 at the center. If I have a derivative going to 0 at the center, if I turn this all the way around and come back on the left side, the derivative will still be 0 at the center. So, the derivative now is continuous as I go from the right or from the left. Okay. So, this symmetry basically requires that the derivative of the temperature has to be 0 as you approach the center. If it is not, since the field is axisymmetric, the temperature derivative will not be uniquely specified. Okay. It will the derivative will be positive on the right side, negative on the right side, positive on the left side. As you approach from the two sides, it goes to two different values. It is not a single valued function at the center itself. The only way that the derivative will be a single valued function at the center is if it is exactly the same, if it is exactly equal to 0 on both sides. Okay. So, that is the physical region for this boundary condition, the symmetry condition that we have here. This will be 0 provided there are no sources or sinks at the center. As I explained to you in the previous case, if you have a wire at the center, there is a source of heat. In that case, the derivative need not be 0. In fact, the temperature, the heat flux and therefore the temperature gradient have to go as 1 over r for the total heat generated to be a constant. In this particular case, there is no source or sink, so the temperature derivative has to be equal to 0. Okay. And this symmetry condition is something that we will encounter often in curvilinear coordinates, both cylindrical and spherical coordinate system. Okay. It just comes out of the fact that one boundary is located along a line or a point, okay, within the domain, and within that domain everything has to vary smoothly. Okay. So, that is the reason for this. Define dimensionless temperatures and radius once again, okay, scaled radius and temperature. Okay. Let me just remove the symmetry argument. Okay. Radius is easy, r star is equal to r by capital R. Okay. Temperature, I can define T star is equal to T minus T naught by T 1 minus T naught, okay, as usual. My original governing equation was dt by dt is equal to alpha times 1 over r d by dr of r dt by dr, expressed in terms of T star and R star. Okay. You can easily check that this becomes dt star by dt is equal to alpha by r square 1 over r star d by dr star of r star dt star by dr. So, this is a scaled equation, except I have not scaled time yet. Okay. However, the scaling of time is now obvious from this equation. Okay. The scaling of time is just given by this. Okay. So, therefore, I can define a scaled time variable as T star is equal to T by r square by alpha. Physically, this is the time it takes to diffuse over a distance comparable to capital R. Okay. So, I have scaled the distance by capital R. The time is being scaled by the time it takes for diffusion to take place over a distance comparable to capital R. So, if I scale it in this way, my equation now becomes dt star by dt is equal to 1 over r d by dr of r dt by dr. Okay. What are the initial and boundary conditions? Boundary conditions first one was that T star is equal to T naught at R star is equal to at R is equal to capital R, which is equivalent to writing T star is equal to 0, because T star is equal to T minus T naught by T 1 minus T naught. So, T star is equal to 0 at R star is equal to 1. Okay. The other condition was the symmetry condition. Okay. dt by dr is equal to 0 at r is equal to 0. Okay. Equivalent to writing dt star by dr star is equal to 0 at r star is equal to 0. and then I have my initial condition, okay, and that was that t is equal to T1 at r at t is equal to 0 for r less than r. Okay. So, t is equal to T1 implies that t star is equal to 0 at t star is equal to 1 at r at t star is equal to 0 for r star less than 1. Okay. So, these are the boundary and initial conditions. Okay. This equation, this problem cannot be solved by a similarity transform, because there is a length scale in the problem, that is the radius capital R. Okay. The way to solve this equation is to use what is called separation of variables. Okay. And we had seen in detail how to do separation of variables in a Cartesian coordinate system. I will only point out what the complications are when we deal with a cylindrical coordinate system. Okay. First things first, when we do separation of variables, we have to make sure that we have homogeneous boundary conditions in all the spatial coordinates. Okay. We had taken care to see that when we looked at the steady state heat conduction between two surfaces. Okay. We made sure that there were homogeneous boundary conditions in all the spatial coordinates. Okay. In this particular case, you can see that we already have homogeneous boundary conditions in all the spatial coordinates. Okay. T star is equal to 0 on one surface, the derivative of T star is equal to 0 on the symmetry axis. Okay. It is only at the initial time that T star is not equal to 0. Okay. It is only the initial time that T star is not equal to 0. Okay. Therefore, we already have a well posed problem. Okay. There is already homogeneous boundary conditions, and there is an initial condition that is non homogeneous. Okay. So, therefore, we can solve it using a separation of variables procedure. Okay. So, let us look at how we would do the separation of variables. Okay. As in the case of a Cartesian coordinate system, we will separate T star is equal to some function of r star times some function of time. Okay. So, this is the usual procedure that is used for all separation of variables problems. Okay. And I insert this into the conservation equation. Okay. And I will get d by dt of r theta is equal to 1 over r d by dr of r d by dr of r times theta. Okay. Now, since r is only a function of r and theta is only a function of time, I can take out the factors r on the left side and theta on the right side. Okay. So, r d theta by dt is equal to theta times 1 over r okay, and divide throughout by r times theta, okay, to get 1 over theta d theta by dt is equal to 1 over r into 1 over r star okay. So, this now is the differential equation that I have to solve, and you can see that the left hand side depends only upon t, the right hand side depends only upon r. So, therefore, both sides have to be equal to constants. Okay. if they were not constants, then I could change t and keep r a constant. The left side would change, the right side would not, and that would destroy the equality. Okay. So, the very fact that the left side depends only upon one independent variable, the right side depends only upon the other independent variable, means that both sides have to be identically equal to constants. Okay. Does that constant have to be positive or negative? Okay. We saw from our experience with the separation of variables in Cartesian coordinates that this constant has to be negative. In particular, I have an equation of the type 1 by theta d theta by dt has got to be equal to some constant. If this constant is positive, theta will increase exponentially in time. If this constant is negative, theta will decrease exponentially in time. Okay. When we solve the unsteady problem, we require that as time t goes to infinity, theta has to decrease exponentially. So, the temperature goes to 0 everywhere. Okay. Physically, we would expect that. I have taken a cylinder of temperature T1, immersed it in a bath with temperature T0. As time t goes to infinity, the temperature throughout the cylinder has to be come down to T0. That means that T star has to decrease to 0. That will happen only if this constant is negative. Okay. So, this constant has to be negative. Let me call it as beta. Okay. So, good. So, we have the constant negative. How do we evaluate the value of this constant? Okay. We put it, insert it into the equation on the left hand side. Okay. 1 over r 1 by r star d by dr of r dr by dr is equal to minus beta square. Okay. So, therefore, if I expand out this equation, I will get d square r by d r star square plus 1 over r dr by dr star plus is equal to 0. Okay. That is the differential equation for r star. Okay. I can multiply throughout by r square, okay, to get r square d square r by dr square plus r dr by dr plus beta square r is equal to 0. Okay. I can reduce this a little bit. I am sorry, beta square. Multiply throughout by r star square. Okay. Now, I can reduce. I can remove this parameter beta, okay, in this equation. Note that the first two terms on the left hand side are equidimensional in r. Okay. They have r square times d square r by dr square and r times dr by dr. Okay. So, they are equidimensional in r. So, if I multiply r by any constant, these first two terms do not change, okay, because they are equidimensional in r. Okay. Therefore, I can make the substitution r plus is equal to beta times r star, okay, and then I will get an equation in terms of r plus as r plus square d square r by d r plus square plus this into dr by dr plus r square r is equal to 0. Okay. So, this is the differential equation we have to solve. If you recall, when we did the same thing in Cartesian coordinates, this term was not there, and therefore, we managed to get a solution just in terms of sine and cosine functions. In this case, there is this additional term present, which means that the solutions are not sine and cosine functions. They are what are called, they are a class of special functions called Bessel functions. Special functions might seem a little difficult to comprehend at first, okay, but they are really no different from trigonometric functions. If I were to give you the sine of some angle and ask you what the value is, you would have to go look up some table. You know the broad features of sine functions or cos functions, where they pass through 0, where the derivative is 0, and how the derivatives are related to each other and so on. Those broad features you know, but to get an exact value, if you are asked, you would have to go and look in some tables. Same thing with Bessel functions. They have and the features, the characteristic features of these Bessel functions are known, but if you actually wanted to know the value, you would have to go and find it in some tables. Okay. So, they are similar to sine and cosine functions, except they are a little more complicated. They do not for example, have a constant amplitude as x goes to infinity, they decrease as x power minus half. They do have an oscillatory form. Okay. In that sense, they are similar to sine functions, but some Bessel functions diverge at 0, some diverge at infinity and so on. The general Bessel functions are solutions of the Bessel equations, which are equations of the form x square d square y by dx square plus x dy by dx plus x square minus n square y is equal to 0. Okay. So, this is the general Bessel equation, and the Bessel function solutions for these are written as y is equal to a1 times jn of x plus a2 times yn of x. Okay. So, these are the general solutions for the Bessel equation, the two Bessel functions. These are linearly independent solutions of the Bessel equation in a similar manner to how the solutions for d square y by dx square plus y is equal to 0 are solutions of the form y is equal to a sin x plus b cos x. Okay. Exactly analogous to this solution for sine and cosine functions. Okay. These are the solutions for the Bessel equation. The Bessel equation has these two solutions. Okay. You can easily see that this equation is identical to this one, except that n is equal to 0 in the equation on top. Okay. So, n is equal to 0 for this equation, and therefore, the solution for capital R R of R plus is equal to C1 J0 of R plus C2 times Y0 of R plus. Okay. These functions J0 and Y0, you can find it in standard texts, okay, in standard mathematical special functions books. Okay. I will just sketch broadly how they look. Okay. Okay. As a function of x, okay, J naught of x, if I plot as a function of x, okay, it starts off at 1 and then it has an oscillatory form. Okay. This amplitude of the peaks actually decreases as x power minus half, as x becomes large, and the frequency tends to a finite value. So, this is the function J naught of x. Okay. The other function y naught of x actually starts at minus infinity. Okay, it has a decay similar to J naught of x. Okay, so, this is y naught of x. Okay. So, the general solution for the Bessel equation is some combination of J naught and Y naught. Okay. Now, first thing we can say is that just from the form of these two solutions, C 2 has to be equal to 0. Okay. The reason is because Y naught goes to minus infinity at R star is equal to R plus is equal to 0. Okay. However, my boundary condition requires that the derivative of the temperature has to go to 0 at R is equal to 0. Okay. So, the derivative of the scale temperature has to go to 0 at R is equal to 0. If the solution had any contribution proportional to Y naught, then that contribution would go to minus infinity as R star goes to 0. Okay. So, just the symmetry condition alone tells me that because the solution Y naught goes to minus infinity at R star is equal to 0, the constant C 2 has to decrease to 0. Okay. So, I require just from the form of these solutions that C 2 is equal to 0 to satisfy B C boundary condition at R star is equal to 0. Okay. Therefore, the solution that I have is of the form R of R plus is equal to C 1 J naught of R plus, okay, or R of R star is equal to C naught C 1. C 1 J naught of alpha R star, no, not alpha, beta. Okay. And this beta is because I have defined R plus is equal to beta times R star, okay, when I did the reduction. Okay. If you recall, when we did the problem of separation of variables in a Cartesian coordinate system, we had a similar solution except it was a sine function, okay, with beta times R star in it. That function beta in that case was determined from the condition that we had homogeneous boundary conditions at z star is equal to 1 and therefore, beta is equal to n pi. Okay. In this particular case, our boundary condition is that T star is equal to 0 at R star is equal to 1. Okay. This fixes the value of beta, okay, because this, if T star is equal to 0 at R star is equal to 1 for all times, this implies that R of R star is equal to 0 at R star is equal to 1. It implies that capital R is equal to 0 at R star is equal to 1. Okay. Since R of R star is equal to C 1 J naught of beta R star, this will imply that C 1 J naught of beta is equal to 0. Okay. This implies that C 1 times J naught of beta has to be equal to 0. Okay. C 1 J naught of beta has to be equal to 0 means that beta has to be one of these values where this curve crosses through 0. It has to be one of those values where the curve crosses to 0. Because if I require J naught of beta is equal to 0, that means that beta has to have a set of discrete values. In Cartesian coordinate system, we had similarly got discrete values because the temperature at z star is equal to 1 had to be 0 and therefore, beta was equal to n pi. In this particular case, it is not n pi, but it is a set of values at which the Bessel function goes through 0, okay. A set of discrete values, discrete solutions of the equation J naught of beta is equal to 0. Okay. So, therefore, the solution beta has to be such that discrete set of beta at which J naught of beta is equal to 0. Okay. and the numerical values of the first few such discrete solutions can easily be obtained from standard books. Okay. For example, I will have beta 1 will be equal to 2.40483, beta 2 is equal to 5.52008, beta 3 is equal to 8.65373, 150, and so on. Okay, you have a discrete set all the way up to infinity. Okay. So, that means that beta can have only discrete values, okay, at which this Bessel function goes through 0. So, these are discrete values at which the Bessel function goes through 0. Okay. So, that is the solution for R. Okay. R is equal to C1 times J naught of beta n R star, okay, where beta n is the set of discrete values. How about the solution for time? Okay. The equation for time is 1 over theta d theta by dt star is equal to minus beta n square. Okay. Which would imply that theta is equal to e power minus beta n square times t star. So, that is the temporal part of the solution. Okay. So, the total solution t star is equal to r times theta, okay, which is equal to c times j naught of beta n r star times minus beta n square t star. Okay. So, this solution for any value of n satisfies the equation. This solution for any value of n satisfies the equation. Okay. That means that the most general solution is one which is the summation of all of these discrete solutions for all values of beta n that I have shown you over here. Okay. For all these values of beta n going from 1 all the way to infinity, the sum of all these solutions is the most general solution that we can get. Okay. So, this has constant C n in it. Okay. How do we evaluate the constant C n? If you recall, when we did separation of variables for Cartesian coordinates, we had defined an inner product, okay, an orthogonality relation, which basically said that the product of the two different basis functions integrated has to be equal to 0. Okay. So, the initial condition that we have here is that at t star is equal to 0, this is equal to 1. Okay. That means that summation n is equal to 1 to infinity of C n j naught of beta n r star is equal to 1. Okay. How do we solve this? We have an orthogonality condition for the Bessel functions as well. Okay. It is slightly different from the orthogonality condition for the sine and cosine functions. Okay. What it says is that integral 0 to 1 r star dr star. Okay. So, this r times dr, that is because cylindrical surface element is r times dr, okay, times j naught of alpha n r star, j naught of alpha m times r star, where alpha n and alpha m, I should use betas here. Okay. Beta n times r star, beta m times r star, okay, where beta n and beta m are two members of this discrete list of solutions. Okay. This is equal to 0 for n not equal to m, and this is equal to half j 1 of beta n the whole square for n is equal to m. Okay. if you recall our discussion of orthogonality relations in a Cartesian coordinate system, okay, we had written that in short notation as Sn comma Sm is equal to integral 0 to 1 dz star sine of n pi z star sine of m pi z star. Okay. In a similar manner, we can define Jn comma Jm for the Bessel functions, the inner product, as integral 0 to 1 note r star dr star, okay, J naught of beta m r star, J naught of beta n r star. Okay. This was equal to 1 half only if n was equal to m and it was 0 otherwise. So, we had written this as half delta n delta n m. Okay. In a similar manner, this is equal to 0 if n is not equal to m, and it is equal to half j 1 of beta n whole square times delta m n. So, this orthogonality relation is the exact analog of the orthogonality relation for the case of a Cartesian coordinate system. The basis functions instead of sine and cosine functions are Bessel functions in this case. That is the only difference. The basis functions, they form a complete set. Any function can be expanded in these basis functions. These basis functions have orthogonality relations, and these can be used to evaluate the constants. Okay. So, this was the boundary condition, the initial condition that we need to evaluate. Okay. Okay. So, therefore, I have the initial condition as summation of Cn J naught of beta n r star, okay, is equal to 1. Okay. Multiply both sides by J m, okay, n is equal to 1 to infinity. Summation n is equal to 1 to infinity C n times J naught of beta n r star, J naught of beta m r star. Okay. And then I integrate this over r dr. Okay. This will be equal to integral J naught of beta m r star dr star from 0 to 1. Okay. The left hand side is of delta m n J 1 of alpha n the whole square. Okay. The right hand side can be evaluated. Okay. You can do that by looking at standard tables or at standard special functions books. The solution, it turns out, is equal to J 1 of alpha n divided by alpha n. Okay. J 1 is the Bessel function of order 1. Okay. On the left hand side, I have delta m n times J 1 of alpha n the whole square from n is equal to 1 to infinity. This is non-zero only when n is equal to m. I should write the right hand side as m. Okay, the right hand side is an integral. So, therefore, I get C m is equal to 1 by beta m, I am sorry, I should get 2 by beta m, J 1 of beta m. So, this is the final expression for the constants. obtained using the same orthogonality relations that we had used earlier. Okay. So, once again, in this case the solution in the spatial coordinates is not quite sine and cosine functions. It is slightly more complicated than a sine and cosine functions. Yet the entire machinery that we had developed, inner product, orthogonality relation, basis set, expansion in that basis set, all of that, the formalism that we had developed for the Cartesian coordinate system still works here, except that I have to define the inner product slightly differently. I have to define the inner product based upon integral of r star times dr star, because that is equivalent to an integral, an area integral in cylindrical coordinates. Except for that, I can use exactly the same procedure to solve for this heat conduction problem in a cylindrical coordinate system as well. Okay. We get discrete eigenvalues in this case as well. There is a discrete set of beta n's. Okay. The values at which the Bessel function passes through 0. Okay. So, that discrete set still carries over for this system as well. Okay. The origin is the same, except that the operator for heat conduction is slightly more complicated. It is 1 over r d by dr of r times dt by dr, and that results in a slightly different form of the basis functions. But the same formalism that we use, the inner products, the orthogonality relations, can still be used in this case as well. So, this completes the separation of variables part of the analysis in cylindrical coordinates. Okay. Next, we will look at a problem of practical interest, that is the flow in a pipe. I said we can get friction factor versus Reynolds number relations for that case. We will derive that in the next class, okay, after briefly reviewing what we have done so far. We will see you in the next lecture.